So good morning, everyone. My name is Fedor Levkovich-Masyluk. I work on integrability, string theory, ADS-CFT, and also a little on matrix models, which is which will be the subject of this series of 4 lectures. So I was told by the organizers, at risk of their fury, that the content should be kept relatively simple. I hope that this will not annoy you too much. So this will really be an introductory course. If you are familiar with matrix models, you may already know these things, but I will assume that that's not the case, and just start from the very beginning and hopefully get to some more advanced topics by the 3rd or 4th lecture or so. So matrix models is quite a fascinating subject in the sense that it requires almost zero prior knowledge. Well, basically just the only more or less advanced thing we're going to need is Feynman diagrams and weak contractions. So I assume you are familiar with perturbative QFT, but so that's a quite unique opportunity in theoretical physics where we can, the objects are very well defined, things can be proven, everything is on a relatively solid ground. And so it serves as a very useful stage where we can explore various very complicated in principle physical phenomena in a relatively controllable setting. So let me say first what actually are matrix models. So by a matrix model we mean a model where we have an integral over matrices with some measure. So the case we're going to study the most is called the Hermitian matrix model. I will first introduce it and then say a few words about why it is important, what we're going to be studying, how it relates to field theory and so on. So Hermitian matrix model. So this is defined by the integral that corresponds to its partition function. So it's an integral over dn. That's going to be the space of n by n Hermitian matrices. And here we have the, okay, so the board is a bit small, so let me try to fit it in one line. So exponent of, let's say, minus s, the analog of the action in field theory. So the action here is s minus 1/2, so minus 1 over 2 gs. So that's going to be a parameter in some sense similar to string coupling constant, so that's why we call it like this. Trace m squared plus, so that's the free Gaussian term, plus a series of interacting terms looking like that. T3 over 3 m cubed plus T4 over 4 m to the 4 plus dot dot dot. So here the GS and T3, T4, and so on, they are all parameters. They are couplings of the theory. Well, GS is more like normalization, but these guys are really couplings. And so in principle, there are infinitely many of them. And so also to demystify this thing a bit, what's the integral over the space of Hermitian matrices? Well, an Hermitian matrix is defined, so m dagger equal m. So that means that we have the independent entries are the diagonal elements, and then real parts and imaginary parts of the upper triangular pieces, mij with I less than j, and imaginary part of the same things. So this is a set of real parameters that parameterizes the space of Hermitian matrices. And so this integration measure is just the product of dmii, just integrations over all these real parameters. dmij, real mij, and dmij. So there's nothing fancy when we say integration over the space of matrices. I mean, when I first learned about the subject, I was a bit confused about that. It's just, they are just parameterized linearly by the diagonal elements in the real and imaginary parts of the rest. Okay, so this is an integral which is very well defined. So we typically the picture you can keep in mind is the couplings in some sense are small, at least initially. So then the leading term is a Gaussian integral. This parameter is positive, so it's -1/2 trace m squared. So it will be basically the sum of squares of all these real parameters. So it's, in other words, if we have an Hermitian matrix, its eigenvalues are real. So trace m squared is a positive quantity. So therefore, this integral is well defined. It's always suppressed at infinity by this exponent. And it's a perfectly valid function. So it's a function of all the couplings, GS, T3, T4, and so on. Right, so now some motivation why this object is important for us if we are studying field theory or string theory. Well, so the basic reason is that this serves as a prototype for field theory in the sense that it's a zero-dimensional field theory. In other words, if you have, say, a Young-Mills theory, then you would have an integral over, well, your fields, which would be matrices in some representation of the gauge group, but also these matrices would depend on space-time. So, and this would be a functional integral. For here, it's literally the same situation, except you don't have any space-time dependence. So the integral is just over matrices. We're just over a finite space of matrices. But nevertheless, so this integral, as we will see, it exhibits various features which also appear in field theory, and some of them are pretty complicated. And here, where everything is well defined, it's a place where we can try to elucidate what are the mechanisms behind the various phenomena. So, for example, well, so it has a non-trivial perturbative expansion. If we have if we can expand it as a series in the couplings, that's what we will focus on today, actually. So there will be some quite rich set of Feynman diagrams appearing from this integral, and they will have some nice combinatoric properties and so on. So, but then also more complicated things can also be studied. One can ask about what is the non-perturbative properties of this function, what are, going in this direction, one can encounter many things familiar from field theory, like instantons, phase transitions, different phases of the theory, non-perturbative effects, and so on.
Here you're thinking of the large n?
No, at the moment, so just a finite n, but yeah, so but the next thing, of course, is that it has a nice large n limit. So where the size of the matrices becomes very big. So this serves as a prototype for kind of ADS-CFT duality. And in fact, the combinatorics that happens here will be essentially the same as in large n gauge theories that have dual string theories. So that's a nice playground where we can see things like genus expansion and so on. So I will explain all this in more detail just to signpost some directions here. So, and also in this limit, so the model becomes typically more tractable, and one can say concrete things about the perturbative expansion. In particular, this allows one to solve various problems of graph counting and connect to problems in mathematics that otherwise would be really hard to solve. So combinatorics and graph counting. By studying this integral. So another motivation is that famously matrix models describe two-dimensional gravity, two-dimensional quantum gravity. So this, to see this, one has to go to certain regimes in the space of the couplings, but the idea is that when you write the perturbative expansion of this model, there are regimes where it will be dominated by very large graphs that also have restricted topology, say only planar graphs that can be drawn on a plane. So and then the sum of when there are regimes when the relevant graphs become very large, and essentially they can be treated as continuous, and then sum over graphs, which are two-dimensional objects, so becomes essentially equal to sum over metrics or geometries. So the sum, or better to say the integral, over metrics in two dimensions, which is the definition of quantum gravity. And some famous universal results in two-dimensional quantum gravity were defined this way for a long time ago, but this direction is still being explored, and in particular, so more recently, some models of gravity attracted a huge interest, like JT gravity, which is essentially gravity in a space with constant negative curvature, so some kind of ADS-like space with some boundaries. And it turns out that gravity in this situation is almost literally equivalent to a model exactly of this kind. Okay, so so these are some pretty concrete directions. Well, and the list goes on and on. So generalizations of this idea leads us to considering matrix quantum mechanics, which is the next step in complexity where this matrix is allowed to depend on time. So then matrix quantum mechanics is so directly connects to what's known as C equals 1 string theory, or CFT. And that's another topic of very active research at the moment. Well, so in addition, so that's one connection to string theory. So then there are other connections, like on some level, the M in M theory can be viewed as a matrix in some deep sense. And of course, there are also connections to pure mathematics. So there are famous relations to representation theory or algebraic geometry, and to various counting problems in geometry like Hurwitz numbers, and so on, which often can be seen from this kind of integral. Okay, so despite the fact that this field originates maybe in the 70s or so, it is still a very active area of research, and it is a pretty important piece of background for a theoretical physicist to be familiar with, at least a little bit. So any questions? So this was just, okay, blah, blah, blah. So, but please, we're going to start doing the actual material in a moment, but please feel free to ask questions at any time. Very happy for that.
What do you mean by that? Since you have a space that...
Where?
Yeah, quantum gravity.
Yeah, here. Yeah, so here the idea is the following. You look at this integral, then you expand it as a perturbative series. It will be given by a series of Feynman graphs. So then there are some regimes when these graphs are restricted to be planar, to be those that you can draw on a plane. Well, that's what the kind of graphs we normally see in field theory in any case, but so they will be planar. And then there will be a further special regime in the space of these couplings where the relevant graphs become very large. Very, very large graphs. So, and essentially they can be viewed as a discretization of some kind of surface, which is discretized, maybe triangulation of certain surfaces, maybe with some disk topology or some, not necessarily on a plane, maybe on a torus, so there are higher genuses, well, yes. And so this will be viewed as discretization of a two-dimensional surface. So we are summing, in the end, not over graphs, but over surfaces. So that means we have a path integral of quantum gravity. Any more questions, comments? Okay. So I assume I'm supposed to use these two boards, basically, right? Yeah, okay, that one I don't really need. Okay, let's stick to these. Right, so let's start actually looking at this integral. So today we're going to be looking at the perturbative expansion mainly. So let's try to work out what are the Feynman rules here. Like what are the propagators and so on. So let's start really from the beginning. So we'll be interested in quantities like correlators. So by correlators, we mean we can take some function, f of n. So well, let's call, for example, something like trace m to the power k, something like that. And so we are interested in its expectation value, which is just integral dm f of m. So let's stick for the second. So let's specialize to the Gaussian model first, where we don't have any couplings. We have just the free term trace m squared. So then this will be integral dm f of m e to the minus 1 over 2 gs trace m squared over, well, I should write this d integral dm without f of m minus 1 over 2 gs trace m squared.
Have an extra minus in the action.
Have an extra minus. Ah, yes, sorry. Yeah, thanks. That's a good point. Yeah, so how do we compute such things? Well, so let's start with a slightly simpler thing where we have not a matrix, but just a regular integral. So suppose we have some integral of the kind integral d or some 2nx. No, not 2n, dnx. So exponent of a quadratic form minus 1/2 x mu a mu nu x nu. Well, with some insertions like x mu 1 dot 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 x mu 2n. So which we can call, if we normalize this by the integral without any insertions, can call this thing the average of x mu 1 x mu 2n. So just a Gaussian integral where we have n variables x that we're integrating over, and so in the exponent we have a quadratic form that couples them with some constant matrix a mu nu, and we're looking at the insertion of some even number of powers. So this will be this expectation value. So so since this is just a Gaussian integral, this is explicitly computable, and probably you have seen this in some form. So the answer is that 2-point expectation values, x mu 1, x mu 2, are the basic object, which is like the propagator, and they will be given by the inverse of this matrix, A inverse mu 1, mu 2. And then if we want to compute the general expectation value, so x mu 1, mu 2n, so then it will be given by weak contractions. So it's a sum over all pairings and product I equals 1 to n over 2-point expectation values between some x's. So we can denote them like whatever, sigma to I minus 1, x sigma to I. So anyway, it's just a formal way of saying that we consider all possible ways to split this into pairings of two x's, like in the usual perturbative QFT. And the result is a sum over all ways of contractions and products of the corresponding expectation values. So well, like one can, if we use this for, say, 4x's, x, 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 so then there are going to be 3 ways to contract them. So I can write this with this plus this and that plus another one, this with that, and second with fourth. So this is something very familiar from QFT, so that's just a property of Gaussian integrals that can be proven in many different ways. Any questions so far? It's just the basic example, integration, expectation values in a Gaussian integral. So how can we use it for our case? So we're going to try and work out the propagator and all that for our matrices. So let's try to unpack in more detail what is this trace m squared. So we are looking at that is integral dm e to minus 1/2 1 over 2 gs trace m squared. So let's try to rewrite it, well, in a way like it is here to make explicit, so which x's couple to each other here. So in terms of the real parameters, we can write it like this. 1/2 trace m squared is 1/2 sum over I m I squared. So the diagonal elements of an Hermitian matrix are real. Then plus sum I less than j real mij squared. So now this one comes without a 1/2, as you can check. Plus sum I less than j imaginary mij squared. Okay, so we have all these real parameters. So these ones just do not couple to anything. Well, okay, so they all don't couple to each other, just a sum of quadratic terms. So this in these variables like mii, real and imaginary part, this matrix is just diagonal. It's just an well, just the okay, the two of the coefficients are slightly different, but there is no coupling between different variables here. And so well, so and then from this you can deduce easily expectation values between objects like real, m, I, j, and say imaginary. Well, okay, this is going to be 0. And then like real mij, real m, kl is going to be, well, just going to be 0 unless all the indices match. So this kind of thing you can work out immediately just from this quadratic part. But what we're actually interested in is not real and imaginary parts, but expectation values of m itself. So mij, mkl. This is the basic correlator that we want to be able to compute. So well, so to compute it, we do the following. So we write m. Well, we have to consider several cases, whether or not these indices are diagonal or off diagonal. And then if they are off diagonal, we split the elements into the real and imaginary part. And we use the known 2-point correlators of real and imaginary parts between themselves. So so this is an exercise that I leave to you. For example, you can consider 2x2 matrices for simplicity. So to derive that the propagator actually becomes the following: GS delta IL delta JK. This is a really important formula that we're going to be using a lot. So GS is this, what I call this, this parameter that was in the action. Well, so you see, since the propagator is normally the inverse matrix, here it was in the denominator, here it will be in the numerator. So that makes sense. And so what's also really important is the order of indices. So this is not a typo, like some people think when they read a textbook on matrices, on matrix models. So I and L couple to each other, and then J and K, which is may look a bit counterintuitive, but actually that's how it will be. As again, you can check on 2x2 matrices if you wish. So I'm not going to derive it. It's really a straightforward exercise in just manipulating these real imaginary parts and so on. So one nice way to represent this correlator. So by the way, I remind again that these correlators are computed like that. So it's the integral with this insertion normalized by the integral without any insertion. That's the standard notation. So how can we represent it as a Feynman graph? So we are going to use what's known as the double line notation, which works like that. So you see these indices are not completely on equal footing, and their order is a bit unusual here. But it all fits very well if we use this notation, ij here, kl here. And it's also useful to draw arrows going in opposite directions. Well, in some sense, they correspond maybe to a complex conjugation, but not exactly. But just I'm not going to explain all the, derive super rigorously all details of these diagrammatics, but you can easily check on examples that using these double line notation will correspond to doing the proper weak contractions by hand. And we'll do a couple of examples in a moment. So that's our propagator, yes. Yes, no, wait. Yeah, actually it should be, I think. Yes, thanks. Yeah, that's a great point. Yeah, I was copying from the wrong question, thanks. L, okay. Yes.
Is it not the opposite way around, like the delta function of the IL and JK?
Well, it is, so IL and JK. So that's like I wrote it here. IL and JK.
So you contract the first index of the first one and the last index?
Yes, exactly. So that's what I wanted to emphasize from the beginning. So this is not, so here it's not a type. Sorry for the stupid typo here, but this equation is completely correct. So the first index couples with the last one, which is counterintuitive at first, but it's a consequence just of this form trace m squared. You can derive it from there. So, so it may look unusual, but in the end, all the diagrams will be very nice. It's not a bug; it's actually a feature. Yeah, the arrows are just a notation. They will help. Well, in principle, that all you need is this equation. After that, you can compute any correlator perturbatively by weak contraction. But so these arrows will help us to represent them graphically, and I suggest just to believe for the second that these orderings of arrows will simply help to draw the pictures in the correct way. So this is our propagator. So again, we're going to be using not single line notation, but so the propagator is represented by two lines. So sometimes it's called the fat graphs, whereas this would be a thin graph. This is a double line fat graph, so ribbon graphs or at Hooft graphs. Okay, so let's compute some examples.
why do you need Hermitian matrices?
Right. So in principle, you can consider more general integrals. But what's nice about Hermitian matrices is that you're guaranteed their eigenvalues are guaranteed to be real. So just writing trace m squared ensures that this thing is positive. And so it's kind of the simplest generalization of usual real Gaussian integral. If you had some general matrix, you would have to say something like m times m Hermitian conjugate to put it here, and then it will complicate the story a bit. But here you are just traces of m to the power n. They are all going to be real objects, and that's why they're nice to consider. So in principle, there are many generalizations. One can consider complex matrices. One can consider rectangular matrices. One can consider models where you have integrals over several matrices at once. But so this really is the simplest one. So let's see how we can compute the, yeah, this one. Yeah, so the nice example, let's try to compute the expectation value for f of m equals trace m to the fourth. And here we're going to start seeing some pretty nice and beautiful structures. So what is trace m to the fourth? So to compute, we want to compute expectation value f of m. So like we discussed, it's going to be a sum over all weak contractions. Okay, you might complain if you're super pedantic that, okay, the weak contraction statement was for the variables which are here, whereas these mij, mkl are some of their linear combinations. But still, the weak contraction theorem is true if you make linear combinations of original variables. So it's all fine. So to compute any correlator, we write it as a sum of all possible weak contractions, and then so replace 2-point contractions by the propagator, and that's it. So how does it work? So trace m to the fourth. So to use this formula, we need to spell out exactly what are the indices. So let's do that. So we sum over I, j, k, l from 1 to n. Trace m to the fourth, so we do mij, mjk, mkl, mli. So I multiply 1, 2, 3, 4 matrices together, and then the last index I make identical to the first one because this thing is a trace. So by the way, an aside, so traces are the most nice objects to consider because, well, they are guaranteed to be real, and they are also guaranteed to have the same symmetry as the original action. So in the action, there was a symmetry where m goes to u dagger mu, with u being a unitary matrix. So this can be viewed as some kind of zero-dimensional version of gauge symmetry for a Young-Mills field, so where you would conjugate your Young-Mills field in this way. Well, here there is no space-time dependence, so it's just that. And the action is built out of traces, which are invariant under this transformation. And also, this transformation, of course, preserves the Hermiticity property. So it's a legal change of variables that keeps the integral invariant. And so for that reason, it's also nice to consider as our observables traces of m to various powers. Right, so coming back to this, so we have this monster. And now we need to consider the sum over all possible pairings. Well, there will be 3 pairings, like in the example with x, 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 x that I showed. So how to represent them graphically? Let's, so we start by drawing this picture in the double line notation. So let me draw it, and I will explain what it all means. So this trace m to the 4 is has the structure of a vertex in our original integral that had all the couplings and so on. That was the quartic vertex there. So naturally, on a diagram, it will be represented by something resembling a vertex. So if I had, say, just the usual phi to the 4 theory, then expectation value trace phi to the 4, I would start by drawing this object and then trying to make some contractions between the legs, because this is a vacuum expectation value, so the legs just will have to contract to themselves. The fields here contract to each other. So here we do the same, but in double line notation. So, and so each of the endpoints here corresponds to one of my matrices. So I draw Mij, Mjk, Mkl, Mli. So then I can draw the arrows like this, like this, like that, like this. So, and you start to see that things are working out nicely here. Sorry about that. Yeah. So these identical indexes, j and j, they live on the same line. So then the orientation on this line just flows naturally. And then, so on the opposite lines, the orientation is opposite on the neighboring lines. And then, like all the picture is completely, like looks completely fine. There is no weird features or anything. So this notation with the arrows is works actually. So here at the moment, we just this picture represents the fact that we have 4 matrix elements, and they are contracted in the shape of this trace. So they are assembled in the shape of trace, not yet contracted. So now we're going to say that we have to, well, for simplicity, we can just write it also like that. So now we're going to have to contract them. So this integral, so this correlator is the sum over all weak contractions. So of which there are 3 here, and it's so more. So it's simpler to first evaluate them directly using this formula, and then look at what kind of picture will correspond to them. So I need to so I have 4 matrices here. I need to consider all possible weak contractions. So I can contract first with second, this with that, or this with that, this with that, or this with fourth and this with that. So just like in the example with 4 axes, there are going to be 3 contractions. So let's spell them out. So the first one is first with second, this with that. So Mij, Mjk, Mkl, Mli. Plus, so next one, I contract first with third. So Mij, Mkl, Mjk, Mli. By the way, the order, of course, doesn't matter. Here, these are just well, variables. I can write them. I can switch this and put it before. They are not matrices here. Plus, the last one is Mij, Mli. Mjk, Mk. Well, and I assume summation of repeated indices, of course. So then to compute this object, we just use this formula. So each of these propagators will be some combination of delta symbols, and one just has to carefully track all the indices. So before we do that, first, are there any questions at this point? So please try to make sure that you understand this, because the rest will kind of build on it. So here we can notice that actually the first and the third terms are the same. If I just identify some indices, then we can notice that the pattern is identical. So for example, so here looking at the first one, so it's MLI, MIJ. So there are two indices which are outside, and one index I which is being summed over. So and here as well, one index is being summed over and two are outside. And here it's the same story. So this with that directly compares. So here was L here, is actually K here. And this Ki outside, there are J and L here. And well, this exactly the same pattern is true for the first term. So I can just, well, since these indices can be renamed in any way, they are just summation indices. So this one I can cross out and put 2 here. So there are actually only 2 distinct patterns of contractions. Let me write the propagator also here to keep it Mij for the future. Is equal GS
The matrices are not symmetric, right?
delta JK. The matrices are not symmetric. They are Hermitian, but not symmetric.
Then the first and third, how are they equivalent? Because in the first, you can see that the inner indices are being like its usual matrix multiplication, JJ, LL.
Yeah, but here also you just have to replace it MLI. If you put it in front, it will be MLI, MIJ. So there are 2 free indices, in this case L and J. And one is being summed over. So it's just a square of the matrix with 2 open indices. And it's the same in the second term, and then they are also multiplied by each other. But if you just look a little bit here, you'll see that the pattern in which they are multiplied is again exactly the same. So it's basically a trace of the square of this. So that's a nice, if you want exercise, to really convince yourself that they are identical. So, right, so we have these 2 contractions to compute, so let's see what they give. Yeah. So just compute them in 3 more minutes, and then we have a break. So let me continue this. Okay, so I use the just this formula and just mechanically replace all the indices. So the first one, so there are 2 propagators. There are going to be GS squared. So what's important is the indices. So here IK and JJ, delta IK, delta JJ. The second one, delta KI, delta LL. And then the second contraction, so here IL, JK, again to GS squared. So IL, JK. And JIKL. Okay, so now I simplify this. Well, of course, we can always simplify repeated summations with the delta symbols. So for example, this IK, KI. This is actually equal to delta II. So let's simplify that. Delta II, delta JJ, delta LL. So in the second one, so here one has to be careful. So let's say IL, then LK, then KJ, and then JI. So in the end, all of 4 of these guys come down to just one delta, delta II. Also, just to be super explicit, I'm using repeated summation in the style IJ, JK, delta IQ. Right, but then what is delta II? The delta II is n. So we have 2js squared n cubed plus js squared n. And so here we already see some structure emerging. So namely, the different diagrams will contribute different powers of n. And let's, after the break, which we will have in a second, we will see how to see this from the diagrams and how this corresponds to a topology of the diagrams. So let's have a 10 minutes, I guess, break.
Before that, are there any restrictions on food for the pizza, vegetarian, vegan, gluten-free, vegetarian? Two?
Vegetarian.
Okay, good. A copy.
Any questions, feel free to ask. Okay, so let's continue. Hope you had a nice break. So we're coming back to the perturbative expansion here. So just to recap, we looked at the expectation value trace m to the 4. So there were 2 patterns of weak contractions. So we computed them, and they are here. So one is n cubed gs squared, the other one is n gs squared. So immediately we see that if n goes to infinity, this is the important one. So and from now on, we will the goal will be to try and see what will happen to various pieces if we look at the large n limit. So one reason why it's useful to know is that these combinatorics that we are looking at right now are exactly the same as they would be in, say, Young-Mills theory if we were looking at the large n limit. So these diagrams, the topology and the stuff that we will consider now, they are exactly translate immediately to discussions of ADS CFT or super Young-Mills and so on. So, so let's try to see what diagrams correspond to these things. So the first one, coming back to here, is when we contracted, so I with K and J with J. So remember, because the propagator has deltas like that, it means we identify I with K and J with J. So on a picture, that means that I start from this thing. Let me redraw it here. So if I identify J with J on the diagram, this means that I close the loop. In the second one, here I identify L with L, so I close it here. So and then I identify, what was it, I and K. So K was here, I was there, wait, this is, yeah. So I was here, K was there. So it's also useful to restore the arrows here, 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 here. So the arrows help you not to make a mistake when doing these things. So I identify K and I. So the way to do it is I draw it like this. So and similarly in the last one I identify, so K with I. So the K, which was, so it all works perfectly. So I identify the I, which was with J originally, with the k that was also with j. So I identify this I with this k. That's exactly what I'm drawing here. So, and for the same reason, I close the other line like this. So nicely, you see the arrows also go in the correct direction. So that's the first diagram. So the second one is going to be more tricky to draw. So this one came with a factor of 2 also. Of 2. So this diagram is completely planar. It can be drawn without any intersection. Well, for the other one, it will be more tricky. So maybe let me leave it as a useful exercise for you to show that the second pattern of contractions corresponds to drawing it in the following way. Oh, okay, so this goes here. And so this contracts there, this contracts there, and then this guy goes underneath, like that. And then it contracts down to here. So if you carefully track which index contracts to which, I'm not going to do it right now, but I leave it as an exercise. So then you will see that this is the picture that you get. So, and it's really important that we keep the double lines at this stage, because they are going to tell us the topology of the diagram.
Is the number is likely to be that because it's going to be
Yes, exactly. That was what I was just going to say right now. So number of closed loops. So each closed loop gives you a factor of n. Why? Well, so for example, let's see here in the first one. So where we contract, so this had, if we write it as a propagator, it had the delta jj. And on the picture, we contracted the line with j and j here, so we obtained this closed loop. But we obtained it from the delta jj. Delta jj is n, so this loop will give you n. And then the same pattern, so basically just contracting these, following these loops, is just going along the delta symbols here. So if there is a delta with this index and that index, then it means there will be on the diagram a line going from here to there. So and in the end, so every closed loop will give a delta with identical indices, so it will give n. So how do we count the loops? So on this diagram, we have this one, and we have the outer one. So we have 3 loops, so that means n cubed. Now on this diagram, so here one should just follow carefully the loop. So let me try to do it. So I go from here to here to here to here, here then below, and then here, here like this, like this, like this, like this, like this, and here close it again until I come back to the starting point. But this is all one big loop. So it's a bit like a Möbius strip or something. So if you follow all the indices, it's a one loop, so it will be n. And that's, of course, what we got also from directly computing the delta symbols. The second diagram had n. So which you can read off from these pictures immediately. So basically, you start by looking at this vertex, and then you look at ways to close the lines, preserving the orientation of the arrows. And if you think about it for a moment, but just sit down and draw this in your notebook, then you will see that these are the only 2 possible patterns. Well, the factor of 2 is a little harder to deduce this way, but it can be done if you invoke some like tricks, extra rules on how to count that. So, right, so we find these 2 diagrams. So each loop corresponds to n, and then each well, each operation where we connect two of these double lines, that gives a propagator. So each, we can call it edge of this graph, that gives GS. So these edges become easier to see if we omit the double line notation for a moment. Well, if you want this graph, you could just represent as like this, click, click. So these are the two edges that we added. So they give GS squared, and the same story here. Anyway, so these edges are pretty clear from the just initial counting. So just from the initial pairing, they are, so then the power of GS is equal to half the number of M's. But the loops are actually important and non-trivial to read off. So this first diagram is what's known as planar diagram. Well, for the simple reason that it can be drawn on a plane, or more mathematically speaking, on a sphere. Well, sphere is equivalent to a plane with one point at infinity, so it's the same. Whereas the second diagram, so it cannot be drawn on a plane, and it's not just some feature that I was not able to draw it. If no matter how you move these lines around, you will not be able to draw it without a self-intersection and on a plane. But it can be drawn on a torus. So it's a non-planar diagram. So I will not attempt here to actually draw it on a torus, but people will, if you have nice geometric intuition, you can probably imagine that. So, well, basically these two loops are going to be the two cycles of the torus. One will, well, I can try to make a kind of sketch here. Because that's an important conceptual point. It will look something like the torus, this. So then I draw this loop like here. And the second one will go like this. So here I should draw it. So this original vertex, let's put it here. It goes here, 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 and then in the invisible part, it closes. Okay, something like that. Hope you get the idea. So we see that diagrams are classified by topology. So some diagrams are planar, they are going to be the most important in the limit n to infinity, as we will see in a second. And then others are non-planar, so they can be drawn not on the sphere, but on surfaces with higher genus. So what's the general rule by which we can classify the topologies? Let's try to see how this exercise would work for a general diagram. So I can imagine that I'm looking at the, so let's say, so the general rule will be like this. So for each graph, so we get, suppose we have a, sorry, so let's start from a concrete formula. So suppose we are looking at the expansion of the partial function, integral dm e to minus 1 over 2gs trace m squared plus some p greater or equal to 3 tp over p m to the power p. So let's think about the perturbative expansion of this thing. So this is just the partition function. So we are computing the bubble diagrams in field theory terminology, just vacuum bubbles without any external legs or anything. So all lines have to close on themselves. So we expand this exponent. So that brings down the traces as insertions in the integral, and then we compute their with contractions using these rules. So just like in the usual QFT. So that will generate a lot of diagrams of this kind. Well, so like always in QFT, we will actually look at the connected diagrams. So if we write this exponent of f, like the sort of like the free energy, whereas this is the partition function. So f will contain the connected diagrams. So connected vacuum bubbles. So let's see also, so why I put this 1 over p here. So that's for the same reason as if you have in the usual field theory something like phi to the power 4, lambda phi to the 4. You divide it by 4 factorial. Whereas here, trace m to the 4 divided not by factorial, but by 4 itself. So the reason for that is that these lines are ordered. You cannot permute them in an arbitrary way. So I will not discuss this maybe in too much detail, but well, if you imagine that you have a diagram with different things like that, so each vertex would correspond to a picture, like this one would correspond to something looking like that, like we already saw. So then the vertex like trace m cubed, so this would be like this, this, this. Well, then, so other vertices would just give a similar picture with n lines coming out. So then if you imagine a diagram where you have different pieces like this with different number of lines and so on, and then you start contracting them with each other. So then, so what happens because of these double lines is that you cannot, well, permute the legs arbitrarily. You cannot say switch this one with that one. Instead, you have to, because of the ordering and the indices and all that, the only thing you can do is you can rotate. If you have a certain pattern of pairings, then you can get another valid pattern of pairings by rotating one of the vertices and then coupling the legs in the same way. But you cannot permute them arbitrarily as you could if they were just a scalar field. So for that reason, the admissible number of diagrams is reduced, and we put 1 over p here instead of 1 over p factorial. Okay, that's a slightly technical point, but just to keep in mind. Right, so that now when we start expanding this thing, so we get a sum over all various kinds of diagrams. So let me draw a couple of them. So if we have a cubic vertex, then we could have something that looks like this. Then, so let's draw a few examples. So this guy is what we already had. This one. Let's draw something else. Here, 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 and here. So this one would originate from 1 quartic vertex and 3 cubic here and 4 cubic. So here, 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 here are all cubic vertices. So let's redraw the guy that we had there. So this one. Okay. And so there will be a huge number of diagrams, of course. So how, when we are given a diagram, how can we compute what is the So what's the general rule by which these powers of n are going to be organized? So the rule is the following. Let me remove that. So each graph will give. So first we have GS to the number of edges. Well, this we discussed. So each edge is the propagator. Propagators have GS. So then, right. So then each vertex. So the vertices come from this action. So the coefficient is T divided by GS. So each vertex will also carry 1 over GS. So we'll write 1 over GS to our number of vertices. So then each loop gives an N. So, and in terms of geometry, loops are actually the same as faces of the graph. So this takes a little getting used to, but well, let's see, for instance, on this example, which is what we had there. So we have 3 loops here, and if we collapse the double lines, this will look like this figure of 8. And then, so in terms of graph theory, so it has clearly like 2 faces, this and that. But also, we should think of it as being drawn on a sphere. So on a sphere, it splits the sphere into 3 parts. This, that, and the outside. So this way of counting shows us that it has 3 faces. And indeed, it has 3 index loops. So that, with this idea of number of faces, this will give n to the power number of faces. So what is weird about this guy? So this guy in that terminology has 1 face. Well, there was this picture on the torus, so you can see that it actually does not split the torus into 2 different disconnected components. All of the outside of this graph is just 1 connected piece. If you think about it carefully, you can see it. So this guy has f equals 3. This guy has f equals 1. Well, which corresponds, of course, to the fact that this is all 1 closed loop. So this one would have 1, 2, and the outside also f equals 3. So this would have 1, 2, 3, 4, and the outside, so 5 faces, and so on. So that's how this vertex, this face counting works. Okay, well, and then, of course, each vertex brings with it also the coupling. So we get, this is multiplied by the product, p equals 3 to infinity, Tp to the power number of vertices of this degree. Well, okay, and then if you want to be pedantic, then there is also 1 over the symmetry factor, which is typical in all Feynman graphs. It's an unknown thing because some graphs have certain extra symmetries which make some contractions redundant. And so on. I'm not going to discuss this. It's exactly like in usual field theory. Like, for example, you probably remember that this sunset graph has some symmetry factor, like maybe 1/6 or so. If you did, might have seen it in some QFT course. Now, this is exactly the same phenomenon can happen for these graphs as well. We're not going to discuss it. These symmetry factors normally are not important at large n. Right, so this is what we have as the contribution of a graph. So we're going to be interested in the large n limit. So So let's try to simplify it. So just combine all the powers. So let's look at So I have gs to the power e minus v. Let me also artificially add and subtract f from here. E minus v minus f. And then n to the f, and this guy that I subtracted, I will combine them. Gsn to the f. Well, times the remaining part, which are these couplings. So they are going to be fixed at large n, so they contribute order O of 1. But this I can, of course, rewrite using that E minus V minus F. So for a usual spherical topology or polygon, that would be minus 2. Well, but in general, it's 2G minus 2, where sphere has genus 0, G equals 0, torus has genus 1, and so on. So genus is the number of holes. So this I can rewrite as G string to the power 2G minus 2. And this GSN, I can call it lambda. So just a second to make sure it's correct. Yes. Okay, so let me call this thing lambda. So I introduce lambda. Lambda is GSN. And so from this formula, we see that it's natural to consider the limit when this thing is fixed, n goes to infinity, and gs goes to 0. Yes, for this one, yes, because all these arrows are drawn in such a way that it will all be nice. I'm not sure if it's possible to get something non-orientable without extra tricks. Not sure about that. So we get the sum of all diagrams. Can recast it as sum over all genuses from 0 to infinity. And we get gs to the power 2g minus 2. And then sum over n, lambda to the n, and the part with their fixed genus and n, well, depending on the couplings. So this kind of expression is what's known as the genus expansion. Well, one way to rewrite it would be in a more maybe standard way to say G string is 1 over n, of course, so this lambda over n. To the power 2g minus 2. So we get immediately 1 over n to the power dictated by the genus. So as genus becomes larger, say for torus or pretzel or whatever, so their diagrams become more and more suppressed by 1 over n. And so actually in this matrix model, this introduction of GS is a bit artificial. So in many textbooks, you can just set lambda equals 1 and G string literally equals 1 over n. There. That's a notation that's also very commonly used. Because, so you see here, this G string can be, if you rescale the matrix itself by some constant factor, then you can reabsorb G string into that. So it's a slightly fictitious parameter, but it's still, well, nice to keep it for pedagogical reasons here to see the clear structure. Still, in many cases, you can just set it to be 1 over n. But, okay, the reason why it is often set to literally 1 over n, not 1 over n squared or cubed or something, is because that's how it appears in the expansion, and the natural fixed parameter is gs times n, like what we had here. Okay, so that's so lambda would be the analog of the 't Hooft coupling in ADS-CFT. And then at each genus, you have a series in this coupling. Yeah, so, well, in terms of the graph, again, G is the genus of the surface into which the graph is embedded. So the surface on which the graph can be drawn without self-intersection. And this is basically the Euler's theorem from graphs. Well, of course, pretty non-trivial statement, but well known. Dun, dun, dun. Well, so we can draw this formula like, so sum over graphs with spherical topology plus G string graphs with torus topology plus higher genus then like that, and so on. And this will have G string squared. So, and that explains the reason for the name G string, because this, so G string is roughly speaking would be the string coupling. In ADS-CFT, that would literally be true. And so then each higher genus is kind of, so sphere is kind of propagation of one single string, whereas this is more like a string that is splitting. So each splitting introduces the G string that couples strings together. And lambda would be the string tension. Okay, these are all just words. Here they become precise if we look at ADS-CFT. So what we have here is just the combinatorics of these ribbon graphs coming from the matrix model. Any questions here?
I don't understand the first diagram here, so.
The first one, this one.
Yeah.
Yeah.
So why is the outer circle there, and which indices are you trying to contract?
Yeah, so it's just like here, there was an outer circle. So this one would come from the following. If I take this, so I have two triple vertices, two cubic vertices. So one is here, the other one is here. Yeah, two cubic vertices this time, like this. So you see, they, so then I contract them like this, this, and so. Okay, yeah, I think that's a good question. So here I basically use the mix of cubic and quartic vertices. But in principle, you have all of them. Right, so and then, so the one usefulness of matrix models is the following. So here, first you immediately see the sum over topologies. If you go to strict large n limit, you restrict to spherical topology. In other words, planar diagrams. So then, and then in various regimes, so at large n, as we will see in the next lecture, actually this integral becomes more tractable, and there are ways to compute it. Not necessarily in closed form, but in some rather concrete form. So, so then one can look at all kinds. If you allow, say, only a few of the couplings, for instance, one could allow only trace m cubed, set all others to 0. So then what you're looking at is triangulations of the sphere. So you would get the sum over all triangulations of the sphere. And if you can compute this partition function, then you can compute the number of such triangulations. So that's a non-trivial combinatoric problem. And then there, of course, then you allow vertices of different degrees. Then you compute splitting of a graph of a given topology into a triangulation or like polygonalization of a graph with given topology with the vertices of a given degree. Well, what I said about triangulation not exactly true. Actually, rather it's a polygonalization of the graph where you allow vertices only of a given degree. So for triangulation, you would have to control what are the allowed faces. There are ways to do it, but not in this model. So anyway, that represents a pretty non-trivial combinatoric problems, counting of graphs of different prescribed properties, as we can already see here. So a few concluding comments. Let me see.
Sorry.
Yes?
How do we know that the small company limit is contains with the mass limit?
Well, I mean, everything here is just perturbative. So we are just looking at the perturbative series and grouping together some diagrams. But in this sense, there is no limit of no order of issues limit. We're not no order of limit issues. We're not making any non-perturbative statements. Just rearranging the terms by grouping together terms with the same power. It's a formal manipulation in a sense. Well, in principle, one can ask this question indeed, and there could be some non-trivial situations where it would not exactly compute, but that would be something pretty exotic. So I wanted to give a couple of exercises that you could compute the diagrams if you want. Just a second. Yes, so let me see here. Yeah, so for instance, a nice exercise is to compute this diagram. That is compute the contribution to partition function coming from bringing down two cubic vertices, and compute this including the symmetry factor. So there will be some quite non-trivial potentially symmetry factor here, which I think is something like 1/4, maybe 1/6 is what you should get. Well, then if you really want to practice more, you can try to compute a few of the others, including their symmetry factors, which will be quite non-trivial here. But so this one, at least is a nice exercise. You should reproduce a symmetry factor of 1/6. So that's one thing. So, and finally, a comment about what happened if we look at actual correlators of some operators, in quotes. So this was so far all about vacuum diagrams, but of course the very similar counting will be true for other observables. So natural observables are correlators of the kind trace m to the power n1, trace m to the power nk. And here, so again, the combinatorics are like in ADS-CFT, and what one can easily see is that the disconnected part and the connected one scale differently in 1/n. So let's see it on one simple example where we look at trace m squared. Dun, dun, dun. One second. Yes. So let's consider, for example, trace m squared, trace m squared. So again, there will be 4 m's, but now like in the example that we did, but the pattern of indices is now different. So that's expectation value, mij, mji, mkl, mlk. So there are 2 options to contract the matrices, basically, that are inequivalent. First option is to contract within each trace. So this with that and this with that. So that would give me delta II, delta JJ. Let me not bother writing the GS all the time. Times delta KK, delta LL. And the second one, which probably appears twice, would be if I contract one matrix from the first trace with one from the second. And the order doesn't matter, as I am pretty sure. So then I get, so this with that, and this with that. So let's see, this with that would be JKIL. And here it would be ILJK. So the first one has n to the power 4. Whereas the second one, so what we get is delta JK, delta JK. That simplifies to delta JJ. So that gives n. And the second one also gives n. So n squared. So the first one was the disconnected one. And the second one was connected. So the first one would, like we saw, the first one is contraction of the fields inside the trace. So this is actually this guy. You can write it like this, trace m squared, trace m squared. Whereas the second actually when you contract between the 2 traces. So you see that 2 things appear. First, the disconnected part dominates at large n over the connected one. And moreover, the correlators at large n, they factorize. So this one is actually just a product of individual correlators. So that's a typical feature in ADS CFT again, where basically the leading part in n is, first of all, trivial in some sense because it is factorized, does not feel the interactions really, and second, it is actually dominating. So normally it's not really relevant. But here you can see the combinatorics where it comes from. Any questions? Yes. 2 in front of it. Yeah, thanks. Okay, that's not super important, but it should be there. More questions? Okay, so yes?
So completely here, if like the second diagram in the perturbative experiment.
This.
Yeah, should appear only when we have a trace of the fourth, or because we have completed that diagram.
Yes, yes, it's yes, yes.
So it appears only when we have in the pure Gaussian theory. This diagram appears.
Well, not really. Well, there we just compute the expectation value of trace M4 in the Gaussian theory.
Yeah.
So that was more like in this kind of logic. But here we are looking now at the expansion of the partition function. So with now not in a non-Gaussian theory, but with non-trivial interactions here. Okay. So then, like in usual QFT, you think about expanding this exponent, bringing down all the terms. So there, in particular, will be a term T4 times m to the 4 in the first order of perturbation theory. So that it will be literally given by the same diagram that we computed. Only now it will be multiplied by T4 and potentially some combinatoric factor, but not here.
And so basically the t to the t power appear only in the function.
Yes, yes, yes. So that the previous one was an exercise to show what are the combinatorics associated with trace m to the n, vacuum expectation value. Whereas here we are computing the vacuum expectation value of 1, but in an interacting theory, which gives the same combinatorics, but
So
yeah.
when we are computing the expectation value of trace of n to the fourth,
Yes.
in an interacting theory, we have to count.
Oh yeah, that would be a separate story. So here we're computing the expectation value of 1. But if you want to do that, that's of course a very natural thing. So here I did the Gaussian theory, but then your Feynman rules would be slightly different. There would be the usual thing. So that would be like a diagram with external legs in QFT. So then you would have these 4 external legs. And then you bring down vertices from the action with many different possible degrees, blah, 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 and in such a way that you can couple these legs with your vertices from the action. So in some sense, this actually corresponds to diagrams. If you have one of these trace m to the 4 or whatever, that corresponds to a diagram with disk topology. Because this kind of, the vacuum diagrams have sphere topology, whereas this one, in some sense, would have a disk topology because, so you contract, say there will be a lot of vertices coming down from this section, and you have to close their lines on each other, except you have to leave, in this case, 4 external lines to connect to your insertion, if you are computing this in interacting theory. So the thing that you have here has to, well, make some planar thing, except for 4 lines sticking out of it. So they, in some sense, they form a boundary of the diagram that connects to these lines. You can imagine kind of this thing sitting above your sphere.
In practice, I have to separate the weak contractor or weak part coming from the interaction.
Yes, yeah, that's a very good point. Yeah, thanks for bringing it up. Yeah, so it works like in usual QFT. So what we consider here is slightly exotic from QFT point of view. It's the bubble diagrams for the vacuum expectation value of 1. Whereas normally we would consider these correlators of traces, and then you can, so you have to bring down all the possible vertices and then connect the legs of your insertion with these vertices in such a way that they all connect and so on. So then you could consider multi-point insertions, trace M4 times another trace of M to some other power and so on. So all these objects are very natural observables. They have important meaning in gravity or in JT gravity or in whatever other problem. And there are many different ways to compute them. So they all will follow the same combinatoric structure with the separation over topologies and so on. And so next time we will actually see how to compute more efficiently at large n by reducing this from integral over matrices to integral over their eigenvalues. More questions?
From the 3-point, from the cubic interaction diagram,
yeah.
You can also have 3 bubbles, right?
This one?
Yeah.
3 bubbles. So that would be, well, I don't know how you could do that. So if you have 3, so you have 2 vertices here, then you have to close all the lines. I'm not sure how you could.
One point, not the 2 point.
For 1 point?
Like from that single, like on the board left view.
Yeah. Yeah, like here. Yeah, you can also do this, yes. I think.
And that would be in
No, wait. Oh, that looks a bit fishy. Wait, that looks very fishy. I'm not sure that would be allowed. I'm a bit worried. Let's see. So if you draw them with the arrows, I think you will see that it's not possible. I think. Here. Well, I mean, from the weak contraction point of view, this cannot be possible because there are only 3 m's. So there is no way. Well, I'm a bit confused now. Well, so you see, the thing is, you cannot close the loops arbitrarily here. You have to connect them not individually, but with the double line again. So you have to connect 2 double lines between themselves.
Okay.
And then you count the loops. But you cannot just connect arbitrarily single lines. So for that reason, you can draw a double line from here to here. That's fine. Going like this, here, here. But then this line would be left completely alone. You cannot connect it to anything. Now that's a nice observation. Yeah. Any more comments, questions? Okay, thank you.